If you're new to this channel, you may consider subscribing and hit the bell icon so that you continue to receive the updates. Also, after watching this video, you may want to refer to some of the playlists that we have created for people who are interested in in-depth knowledge. These are the videos in the right sequence, which will give you thorough knowledge of the subject. Please share it with all others who might benefit. Let's get started.
So far, we've talked about what are activation functions and what makes them good activation functions. In fact, we compared some of the popular activation functions through a grid like this. But there's one important activation function which we have not talked about, and that is known as the Softmax activation function. What makes it different from the other functions? Why is it that this is popular only at the output layer? We're going to look at it very closely in this video, and you'll get answers to all these questions. First, let's go back to the scenario of binary classification. Let's say we have this arrangement. We have an input layer which has just 2 inputs. We have a hidden layer with 5 neurons, and we have an output. Now, we've already seen multiple times that in a forward pass, you start with the inputs, you do aggregations at each neuron, you apply an activation, and you keep moving forward. If you refer to just this output neuron, there is an aggregation that's happening here, which is, let's say, Z, which is based on the inputs coming from all these 5 hidden neurons, and it undergoes some kind of an activation function. Now, if you're dealing with a binary classification, the preferred activation function used to be the sigmoid function, where the formula for this is 1 over 1 plus e raised to the power negative z. And this used to be a value like a probability, always ranging between 0 and 1. We very closely examined all these activation functions in our previous tutorials. And how do we get the value of y hat in this case? So it's based on a decision rule. If this expression evaluates to a value which is greater than or equal to 0.5, we used to say this is class 1 or the positive class. And if this used to evaluate to less than 0.5, we used to say this is the class label 0 or the negative class. Simple decision rule based on a sigmoid. But we don't just solve problems which are binary in nature. There are times when we are solving a problem which could be more complex. For example, we could be trying to predict an action related to the stocks. So we could have a decision which is buy, the other decision could be sell, and the third decision could be hold. And it's not that we have to decide only for 2 or 3 levels. In fact, one very popular case study in deep learning is the handwritten digits case study, where we have to predict the classes from 0 to 9. These are digits from 0 to 9, and we have to identify. So you can imagine, in those cases, have 10 neurons here at the output. So we are talking about a scenario where we're solving a classification problem, but it's beyond the binary classification. We have multiple possibilities as the classes at the final stage. So in such cases, you have aggregation happening at all these output neurons. So let's say this one from these 5 hidden neurons is Z1. Likewise, here it's Z2, here it's Z3. Now, the question is, how do we figure out what should be this activation function F? What are the requirements we'll have in mind? First of all, these outputs that we'll get, we prefer them to be like probabilities, like P1, P2, P3, because probabilities are always more relatable. When we say something is a 0.4, we know it's a 40% chance of happening, right? The other condition that we have to keep in mind when we are looking at the output is that these probabilities should add up to 1, and that makes it a probability distribution. So this is one restriction that we are putting, that the probabilities should add up to 1. While this is favorable for the outcome prediction, but if we use this for the hidden neurons, we will run into a problem. We know that hidden neurons are supposed to be independent of each other. But if we impose a condition like this, that the outputs coming from the hidden neurons should also add up to 1, then we will not allow them to make the decisions freely. And that is the reason you will see softmax is only used at the output layer. You would not see this being used at the hidden layer stage. And it's particularly used for cases of multi-class classification. So we clear that we want the outcomes to be like probabilities, and they should be like a probability distribution, which adds up to 1. But then how would we make our prediction? The answer is simple. We will do the argmax of P1, P2, P3. What is this argmax? It will point to the class which has the maximum probability. So for example, let's say these are the predicted probabilities, the P1, P2, P3 values that we have. And you can see in this case, they're all like probabilities. That is, they are between 0 and 1. And they also add up to 1. Now, what would be the prediction? So if you do an argmax of P1, P2, P3, you will say that my predicted class is the class 2, which has the highest probability. That will become your y hat value. So in this case, if we talked about this as buy, this as sell, and this as hold, then you will say the recommendation for the given stock is sell, because that is represented by class 2. Now let's look at the mathematical expression of softmax function. So it looks like this. So softmax, if we give an input in general zi to it, it will be something like e raised to the power zi exponent of zi divided by sum of all the exponents. In this case, exponent of z1 plus exponent of z2 plus exponent of z3. And you can imagine if it's designed like this, it will satisfy being between 0 and 1 all the time. And if we add all these possibilities for z1, z2, and z3, we will get 1. So it satisfies both the conditions that we wanted it to satisfy. If you look at these specific expressions, for each class, we have a predicted probability, which is calculated like this. But now let's also evaluate the softmax activation function through our magnifying glass. Remember, we did this for every single activation function. So what are the properties of the activation functions? Is it nonlinear in nature? It is. Let me show you the graph. It looks a little different compared to the usual activation functions. Why? Because remember, we are making use of the same function at 3 different places. We are using it for class 1, we are using it for class 2, and class 3. These all are different curves. While the activation function is softmax, the response based on the inputs that we receive, based on the z1, z2, z3 inputs that we receive, looks like this. So it is nonlinear. That's very clear. It's not a straight line that you're getting here. That's kind of sorted. Differentiability. Do we have differentiability in case of softmax? Let me show you the differentiability here. So you can see these are the derivatives that we have for the softmax. For each class, again, we have a different derivative, as you can see. So softmax is also differentiable. Of course, it has to be differentiable because the whole idea of backpropagation depends on the differentiability of the activation functions. So it is differentiable. Zero-centeredness. No, it is not centered at 0. We saw that in the graph. Computational efficiency, it scores a low here because you're using exponents time and again, both in the numerator and denominator. So it's computationally expensive. And that's why, again, it may not be a good idea to use it at the hidden layers because it would increase the computational load. Saturation effects. Yes, we do observe saturation effects in case of softmax as well. So there are ways to overcome that. For example, we may try to overcome that by ensuring that at all stages we give a normalized input, which is very range-bound. And we may also use something called as a gradient clipping, which limits the gradients to a certain range where they do not end up becoming saturated. So we've understood what a softmax activation is, why it is not suitable for being used at the hidden layer stage, and how is it different from the other activation functions. We also looked at it through the magnifying glass, and we now understand what are the strengths and weaknesses. Hope this helps.